Okay guys, my name is Titi Malevo, the Physics 131 lecture. Physics 131 lecture. So today we're going to cover the new chapter, which is chapter 7. Chapter 7, using the 7th edition of John Cody, which is the 7th edition. So we're studying a new concept called linear momentum. So this video will serve as an extra class. So some of you, they ask for extra classes, so I'm providing you an extra class. So before we can talk about the linear momentum, we will talk about what is called the conservation of momentum. This is one of the fundamental aspects of physics that is very important. So we should spend some time discussing it and solving the problems regarding the concept. Before we can talk about this conservation of momentum, we spoke about the Newton's third law. And we said this Newton's third law is an action-reaction. It's an action-reaction law. In other words, you have two objects of different mass. This object is exerting some force to object B, and object B is also responding with the very same force but in the opposite direction. So we write F of A, the force of A, and is exerting a force to B. And B is also responding with the very same force but in an opposite direction. And all the process is called the action reaction. So we're going to use this action reaction in the conservation of momentum. So in the next minute we should see how this is applied. So before we can talk about this conservation, let's introduce what we call the force. Force and momentum. By now you should be knowing what is force, and the force is a vector which has both magnitude and direction. So according to Newton's second law, F is equals to m multiplied by an acceleration, which is also a vector. You're applying a force to an object with mass m, and there will be an acceleration, there will be a change in velocity over time. We also know that an acceleration is equals to dv over dt. This is from the kinematics equations. So we can substitute our A in the second law, where F is equals to the mass multiplied by dv over dt. This is also a vector. So assuming that you're applying a force F to this object with mass, and there will be a change in velocity over time. If you apply the force and the mass doesn't change, we assume that the mass is constant. Therefore, we can rearrange this formula as F is equals to d over dt, then m multiplied by v. So there is a new concept here, and this we called the momentum. So this momentum will be given a letter P. So if F is a vector, therefore the momentum also needs to be a vector. The equal sign means they are equal, so it should be both vectors. So this can be rewrote as dp over dt. So what does this equation tells you? You're applying a force F to an object having a mass m, and there will be a change in momentum. Or if there is a change in momentum over time t, it means you have applied a force F. So you can solve for momentum multiplied by dt both sides. So F dt is equals to dp. So you can integrate both sides. The integration of dp is equals to the integral of f dt. So if you are integrating dp, in this case you will have change in p, the integral of f dt. So again, this change in dp is known as an impulse. And it will be given a letter J. So let me rewrite it. You have change in P, the integral of f dt, and this is your impulse with letter J. So the equation can be arranged as follows: J, which is a vector, equals to the integral of f dt. It's an impulse. This can be represented in a graph in this manner. You applying a force, let's say force x in the x direction over time t in second. This one is in Newton. Your impulse will be the distribution so the impulse will be the distribution under the curve. We are integrating the force over dt. You can also apply, in this case you can see that the force is distributed all over, so you can also apply a constant force. So if we apply a constant force, we say in J is equals to the constant force or the average force dt, the integral, or you can write J equals to the integral, instead of this curl bracket, you're using the bar dt just to show that it is constant. So this can be represented in a graph like this. You're applying this force at time t, at second. So you're having the very same distribution between T1 and T2. So you apply a force which is constant, and the impulse will be the area under the curve. So let's see if you understand. Let's do an example that should bring you into speed. This is an example. You have an object, let's say a box, and you're moving this box to the right, and the velocity, initial velocity, let's give them a value, let's say 2 meters per second, and this box has a mass. You can give them a random value of 0.5 kg, and there is an impact force acting on this object, which is a box in this case. So what is the final velocity? You're having an object, box A, that is already in motion with this velocity, and there is an impact force that is acting on this object. What is the final velocity? Let's represent this using a graph. This is time in second. This is F, it moving to the right. Let's say it's a positive X. So during this short period of time, changing t, there is a force that is being applied. I'll say this is changing t. Let's give it 0.5 seconds. So you're applying a force, let's say of -3 Newton. So as you can see, you have a force which is -3. You have change in t, which is 0.5 seconds. You have V, you have a mass, so you need to calculate the final velocity. So our J is equals to the integral of force dt. So if you integrate this irrespective to t, you have F change in t, which is the impulse. This can be your equation 1. But we also know that J is the change in momentum, which is mv2 minus mv1. So the mass is the same for both. It doesn't change the mass. So you can substitute this into this equation, this being your equation 2. So you can substitute this here. So you have mv2 minus mv1, which is equals to F change in t. So now you can solve for v2, which is the final velocity. So how do we do that? v2 minus v1 equals to F, it's F change in t. We divide with mass both sides, divide by m, you divide by m, so m and m cancel, you'll be left with v2 minus v1 equals to f over m change in t. So v2 is equals to f over m, change in t plus v1. So you have equation 3. So you can now substitute the values. So let's see what is your final velocity after the impacted force. So this is minus, the force is minus 3 divided by the mass, which is 0.5. You multiply by 0.5 plus the velocity, which is 2. So this and this cancels. Minus 3 plus 2, which is minus 1 meters per second. So v2 is equals to this. So we can plot this just to check. You have this object moving at v initial, which is equals to 2 meters per second. Let's say the direction is that time in the positive x-axis, and along the line there is this force acting on this object. This is an impact force of which is minus 3. So if it's a ball, we can say it bounced back, it hit the force, and it bounced back with minus 1 meters per second. I hope it makes sense. Now let's talk about this conservation of energy and momentum. Conservation of energy and momentum in collision. Whether the energy will be conserved or not after collision. Let's go back to our Newton's third law. You have an isolated system. In an isolated system, you have, let's say, a number of particles. If we have a number of particles in the system, according to that law, all these particles, they are interacting. All of them, they are interacting. So the interaction between these particles can either be gravitational or electrical. But there's an interaction that is going on. So if this particle is interacting with this particle, there is an exchange in forces. This one is acting on this one, and this one is acting on this one. So there is a force of interaction between the two. And also there are forces around, meaning this might be interacting with this one, also interacting this one, and also this one is responding, this one is responding. So you can see you have 1,000 number of particles, but you can be able to determine the total momentum of the particles that are involved. So how do we do that? The total momentum of all the particles involved is equals to the sum of all the particles. If there are 1,000, the sum of all the 1,000 particles that are involved here. So you have P1, let's say this is 1, this is 2, 3, 4, and so on and so forth. So you have P1 plus P2 plus P3 plus P4 plus, there are so many, so you can represent as plus P, Pi, where I is a number of particles. And this can be simplified by writing it like this: total, which is the sum of all the particles and the momentum that are involved. So for simplicity, let's just take 2. You have this object, or a particle 1 and a particle 2. So during the interaction, they are colliding. This is exerting some force. This is exerting some force, responding, let's say F12. This one is F21. So there's an exchanging in forces. So there's an interaction. So during the collision of this, they will collide. So during the collision, there are 2 things that are happening. Is either after collision, the particle, they don't stuck together, and we call that an elastic collision, or they might stuck together, and we call that the inelastic collision. So in an inelastic collision, this is what we called the conservation of energy. We have the conservation of energy. Obviously here it's the opposite. So there is an energy loss. Let's make a simple scenario. Let's say you have a ball. You throw this ball with some energy of 10 joules. You throw it down, you bounce it with this 10 joule. Assuming that it returns to the same position with an energy of 10 joules. This is unlikely to occur situation, but for simplicity and illustration purposes, we'll say it went back to the same position with 10 joules. So you see the energy before is equals to the energy after. In other words, there is a conservation of energy. This is just a fancy ways, guys, of saying there is a constant energy, or the energy does not change. In the case of the inelastic, there is an energy loss. So you have the same ball, you throw it down with 10 joules. So instead of bouncing back, probably stuck somewhere here, and you calculate and you get that there's 0 joules on it. So you can see it lost about almost 10 joules in total, from 10 to 0. So there is an energy loss during the collision, after collision. So we call that the inelastic collision. So you can calculate the momentum before and the momentum after collision. So you have this ball and this one. different mass, A and B, so they collide, and after collision, let's say they repel, they move away from each other. So MA, MB, this will still be MA, MB, this is VA, VB. So after collision, we say it's VB prime, VA prime, just to distinguish between the final and initial velocity. So what's happening here? You have your M1, you have your M1, which is MA plus VA plus MB VB, which is equals to MA VA prime plus, actually it's yeah, and MB VB prime. Because the collision is assumed to be elastic, so the kinetic is also conserved. The kinetic energy is also conserved. So we can represent that as MA VA squared plus half MB VB squared equals to half MA VA prime squared plus half MB VB prime squared. Let's just give them random values. Let's say MA is equals to 1 kilograms, MB is 2 kg, and the velocity, let's give this VA 5 kg, meters per second rather, we misspoke. VB is equals to 3 meters per second. So you can substitute the values here. It's half, this is 1 multiplied by 5 squared plus half, this is 2 multiplied by 3 squared, which is also equals to 1 multiplied by 5 squared plus half of 2 multiplied by 3 squared. So if I punch in the calculator, 0.5 into 1 multiplied by 5 squared plus 0.5 into 2 multiplied by 3 squared, and you get 21.5 joules, assuming this will be 21.5 joules as well. So the kinetic energy before is equals to the kinetic energy after. So there is a conservation of kinetic energy in the elastic collision. Now let's go back. You have an object A and object B. They are interacting, and after collision they start together and they now move with the same velocity because they are glued together. So how does the kinetic energy changes after collision? So we can start with the momentum. So the momentum of A, VA, plus the momentum of B, VB, is going to be, they are now coupled, so it's going to be the mass of both MA plus MB multiplied by a new velocity, because they are now moving with the same velocity because they are coupled, they are glued together. So you can determine what is your V, final velocity in this case. So let's just plug in the values. So this is 1 multiplied by 5 plus 2 multiplied by 3 equals to 1 plus 2 multiplied by V prime, and 1 times 5 is 5 plus 6, 3 V prime. So this is 11 over 3 meters per second, which is V1. So this is the final velocity. So let's see whether the energy is conserved or not. So I'll just write it here. You have half MA VA squared plus half MB VP squared, which is equals to half the mass are coupled MA plus MB times V prime squared. So this we calculated and we got it 21.5 joules. So you can calculate the other side. 1 over 2 M, it's 1 plus 2. You have your V, which is calculated, is 11 over 3 squared. So 21.5 joules is going to be, let's punch in the calculator, 0.5 to 3, 11.3 squared, and it's 20.2 joules. So you can see that the kinetic energy before is less than the kinetic, is not equals to the kinetic energy after collision. So this is said to be inelastic and the energy is not conserved. The energy is not conserved. So by now you should be able to distinguish between the inelastic and elastic collision. What happens when the collision is elastic or inelastic. So let's do another example. You have two 5,000 kg train collide and stick together and stick together after collision. So you are required to calculate the common velocity. So you have this train colliding with the same train of 5,000 kg. This one is also 5,000 kg. So after collision, it said they are stuck together. So the total mass of this train now it's 5,000. So the total mass 5,000 plus 5,000, that should be 10,000. It's 10,000. It's 10,000 kilo. So we're now interested in the final velocity of these two. So we are given that the velocity of this one is 24 meters per second. This one, the velocity was 0. In other words, it was stationary. So we can calculate the final speed. So m1 v1 plus m2 v2 is equals to m1 plus m2 multiplied by the v final. So this is 5,000 multiplied by 24 plus m2 5,000 multiplied by v2, which is 0. This is 5,000 plus 5,000 is going to be 10,000 times vf. So you have 5,000 multiplied by 24 . It's 120,000, which is equals to 10,000 vf. So you can solve for vf by dividing by 10,000 both sides. So this one cancel off, and this should be 12 meters per second. It's 12 meters per second. So the final velocity is 12 meters per second. So another question is this an elastic or inelastic? Is it elastic or inelastic? So to determine that, you can find the kinetic energy before and the kinetic energy after. So we can say F mv1 v1 squared plus half m2 v2 squared, which is equals to half the sum of masses times v final squared. So you substitute the value, half 5,000 multiplied by v1, which is 24, and you square it, plus half 5,000 0 squared half of 10,000. You have your v final, which is 12 squared. So this one is automatically 0. So you can punch in this one, 0.5 times 5,000 times 24. You square it, 144,000 equals to 0.5 times 12. You square it, it gives you 72,000. This is in joules. So you can see this 72 is probably the half of 144. So there is a loss in energy. There is a loss in kinetic energy. And if there is a loss in kinetic energy, we say that is an inelastic. Collision. Therefore, it's an inelastic. Okay, I think this should sum up all what we need what we need to know for this lecture. So let's meet on the next lecture. Thanks.